Oh, didn't work. Oh, yes, it did. Hello. Welcome to the Happy Maths Hour on Monday, the 8th of March. I'm here with Toni as usual, and today it's all about ups and downs. But first, just after we have the initial break, we're going to celebrate women in the world today, and for International Women's Day. So happy International Women's Day, everybody. And we'll see you after the break with a few examples of extraordinary women in our world.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us, 24 hours, and let the happiness come to you on Relax Radio. Tune in to Relax Radio. Relax Radio.
Hello, Caroline.
Hello, welcome everybody. Hello, welcome Toni to Happy Maths Hour. And I pressed the share screen thingy too soon. So we're teeny weeny itsy witsy, and the women for International Women's Day have got the big screen. And Toni's thought very carefully about who we can celebrate today. So go ahead, Toni.
Well, there were so many women, but I decided that I just pick a few. And these three ladies are quite well known now, I suppose, through this film. But for many years, they were just taken for granted, I suppose. But in the day, in 1969, when the first men landed on the moon, there were not computers, and the way we know them today. Computers at that time meant people who did the calculations. The most prominent women in that team were Katherine Johnson, Dorothy Vaughan, and Mary Jackson. So I do recommend this film, Hidden Figures, if you haven't seen it. It's a remarkable film about three remarkable ladies. And there they are in the front of the picture there.
Now, weren't you a computer at some point, Toni?
Well, yes, I was, I suppose, but that was when I was 15 and I did a holiday job in the school holidays. And that was even before the days of anything electronic. And I just wound a handle on an old Brunswiga machine. Yes, and now I picked three more ladies. And these two, Ingrid and Maria, were actually physicists. I mean, they were, but the thing is, there's a very thin line between mathematics and physics, and mathematics is needed in all the sciences. So I picked Ingrid, who's still alive, and she's a Belgian physicist. And she has done some amazing work on image compression technology. And then Maria Goeppert-Mayer, she was born in Germany, and she won the Nobel Prize for Physics. And her work was on the atomic nucleus. And she was only the second woman to win a Nobel Prize. An amazing woman. And the third one, Mariam Mirkazani, she died very young, very sadly, really, because she had a brilliant career. She was born in Iran, but then she studied in America and became a professor at Stanford University. And she was the first woman ever to win a Fields Medal. So I don't know whether you know, but there's no such thing as a Nobel Prize for physics.
For maths.
For maths. Yeah. Of course, there's a Nobel Prize for physics.
Yeah.
But there's no such thing as a Nobel Prize for mathematics. Instead of the Nobel Prize, mathematicians have the Fields Medal. It's the top award in mathematics. And Mariam won that for her work on the study of dynamics and geometry of Riemann surfaces. So 3 more, 6 altogether, really impressive women. So we're just celebrating International Women's Day by talking about these women, but I could have chosen, there were many more people I could have chosen who had remarkable careers in.
I'd like to add one to the list, if I may.
Oh, please do.
Yes. Her name is Toni Beardon.
Oh, no, come on.
Yes, no, I'm going to, because I have in my world, there are lots of maths women in my world. And Toni isn't just about doing maths and doing extraordinary things with maths. Her passion, I'm talking about the woman that's right here with me. She actually makes such a difference. And it's not about just the ones, because I am not very good at maths. Toni's finding more and more just how rusty my maths is. But what Toni is amazing at is creating resources that help people learn maths, and not just that. She's very conscious about the disadvantaged people. So if you're in a community where you could do with some really rich mathematical activities that don't require expensive resources, where you can use things like paper and string and tape, and yet you want to learn solid mathematics and great ways of learning it, Toni has created twice, not once, but twice, websites where this can happen. The first one requires more technology. The second one, Aiming High, is something where you can just download a PDF on a mobile phone and use that by creating the resources and doing the really rich mathematical activities. And that's Toni Beardon right here. So this is woman number 4.
Caroline, I'm not really a mathematician. I'm a teacher first and foremost. And I've been so excited to live in the age of the internet, because way back in 95, when I really became very excited about this new thing. I mean, funny to think about it now as being new, but it was then. And the idea of sharing maths with other teachers and children around the world, that was so exciting. So that was what I did first of all with Enrich. And then, as Caroline has just said, technology has changed. So now what we needed computers to do, people can do on their cell phones even. Still computers are very useful, but now, whereas for many years, it was very difficult to reach people in disadvantaged communities because they didn't have the bandwidth, they didn't have the connectivity, they didn't have the hardware. Now it's changed in the last 5 years, which is so exciting. So I think we want to go on to our topic for today, which is, well, ups and downs, but it's more than that. It's curves and lines that we see and are important in our lives. And here I've collected 5 pictures from sport. Now, first of all, in the tennis, the man's about to serve. You can see a lot of straight lines there. So in our environment, a lot of our buildings and things that we construct use straight lines. And in the cricket, you see there that the stumps of the wicket, they are straight. But once you hit or kick a ball, or throw it into the air or some other object, it travels in a curved path, and that's called a parabola. And you can see there the sketch. The bowler is the man who throws the ball, and it's in that picture you see the path is a parabola. It lands and then bounces up again, and a smaller parabola, and the path is then this curved shape. So, and it's very similar to the curve that the golfer is he's hit the ball and he's hit it so that it goes over the water to the green on the other side. And then, of course, the footballer wants to get that ball to another player, or better still, into the goal. Serving in tennis. I was hopeless at tennis. How about you, Caroline?
Every single tennis racket I ever used had a giant hole in the middle, because I would swing that tennis racket and every time the ball would go straight through it.
But you see, we're not actually doing maths in our heads when we hit a ball, or with a racket or a cricket bat or a golf club, or throw it. We somehow, human beings, have got this built-in calculator which helps us to put the ball in the right place.
We estimate based on experience.
Yes, I think so. I think we practice until we know just how to hit the ball or to move to get the ball where we want it. And of course,
learn, the mechanics of our body, we learn it's a feedback loop. It's what to do with your body and then to predict what's going to happen when you do it. So if you hit a particular ball in particular conditions, if you do it enough times, you can repeat, you can make sure that what you do is repeatable. And that's why professional athletes are so successful, because they do it so many times. And also constantly improving. We were talking about that with Asif just in the last one. It's learning from your experience and improving.
And it's also having a good coach who watches what you do and who knows about the techniques and who is able to tell you, analyze what you're doing, and able to tell you just what to change. A lot of it is instinctive, but a lot of it is also having a good coach, I think.
Which same goes for having a good maths teacher. So they can actually recognise where the problem, if you're not getting something, a good maths teacher can figure out what it is you're not getting.
But actually, this is very, very important comparison, because this is about doing something. Somebody who's your teacher or coach watching you and then helping you to do it more successfully. It's not, learning is not, as it has often been in many classrooms, it shouldn't be, but this is how it often is, listening to somebody and remembering what they say. I think we come back to this week after week, don't we, Caroline?
Yes.
That sort of knowledge that can be stored in a computer is of no use at all unless it can be applied. And to apply and use that knowledge, you've got to be able to understand it. And that understanding comes through doing, not just through memorizing. So I think we've come up to the time for the break. And after the break, we'll look at some more sports and some more curves.
Thank you, Toni. See you after the break. Sports and curves.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us here 24 hours and let the happiness come to you on Relax Radio. Tune in to Relax Radio. Relax Radio.
Well, I like this picture of the little boy, don't you, Caroline?
I think it's wonderful, and he's concentrating. He's got one little eye closed, and he's got one. It's really concentrating. Look at that face.
Yes, and he does so want to hit the target. And there's nothing sharp on the end of his arrow. It's got a sucker pad on it so it can stick on the target. And an interesting thing there is he is aiming it slightly upwards, so it will go up because it will inevitably fall a little if he were to shoot straight at the target, it would probably drop before it reached the target and go below the target. So there he is. And now the woman in the middle, she's doing shot put. And she's got the ball by her neck, but any moment she's going to straighten her arm and throw the ball as far, well, it's heavy, isn't it? A shot is very heavy.
Very heavy.
She's going to throw it as far as she possibly can. And when it travels, it will be again a parabolic path. But the woman who's doing the high jump there, she is making that curve with her body. And it doesn't look from that picture as if she is actually going to get over that pole. But I believe she will. I mean, she's
still headed upwards, isn't she? If she were headed backwards, then she wouldn't. But if she's still going up, then she can still do that.
She's going to go up and over in a big arch, and yes, and she is going to land on the other side without knocking the pole off its rests. And then the man who's kicking the ball, I wonder if he's kicking at goal. I don't know, actually.
No, he looks as if he's on the side there.
Yes, and now.
But that was one of the things that I was musing over we've been preparing this, and that was one of the things. Is as long as, whether it's a human being or a missile or a ball or a book, as soon as it's released, if you throw it or something causes it to move, once it's released, as soon as it's released, it follows a parabolic path.
Yes, and that motion has got two components to it. Now, the horizontal motion doesn't change unless, it's sort of traveling through something very thick. I mean, or there's a very strong current or wind or something. But in general, there's almost no change in the horizontal motion. Nothing, and friction may slow it down horizontally, but in general, it goes at a constant speed horizontally. What makes for this parabolic path is the fact that the gravity is acting on everything in this world. There's gravity acting on it once it's up in the air. Gravity, well, even if it is standing on the ground, there's still gravity pulling it down, keeping us on the ground, keeping us on the ground. Now, here we've got some rather fun photographs of water slides and skateboard park and roller coasters. So these roller coasters, they're not actually parabolic, but we've put them in here because they're curves and they're certainly ups and downs, and they are carefully calculated, because otherwise the car with all the people in would just shoot off. I mean, there's a lot of mathematics there in calculating exactly those bends in the roller coaster.
I've been finding out some things about roller coasters because of doing this. There are some cars that are actually attached to the rails and do things that are the car would not stay on, but there's others that do rely on literally the curvature and the speed, and a very, very nifty engineering involved in creating them, where it's absolutely critical that the speed and the shape of the curves is just right.
Well, I guess, Caroline, what you're referring to applies to the one in the middle, which actually does a loop the loop, and at one point everybody in the car must be just hanging down. That must be terrifying.
Well, the centripetal force keeps you in place, and actually it's weird because the loops for me are the least scary of the parts of the ride. You don't realize it goes on so fast. You think, what happened? It's the ones where you go down and you're going down, you can see you're going down, and you keep going down. Those are the ones that really scare me.
And then if it's calculated, it will be calculated accurately, so that when the car gets to the top of the curve, it's almost stopping, and then it goes over the top and gathers speed as it goes down to the bottom of the curve, and then it's got enough speed at the bottom to take it to the top of the next curve, which is all very clever. The skateboard park is rather similar. I suspect that is got a flat bit in the middle, but the edges are probably parabolic. They're curves. I mean, of course, it's there's a lot of space there, so we're just talking about a slice through it, and that is calculated so that, well, the ones at the front, slopes at the front are not quite as steep as the slopes at the back of that skateboard park, and when you skate down, you have just enough gathered because of gravity, enough momentum to get you to the top and onto the platform, and a good skateboarder can jump onto the platform on the other side, and that's very enjoyable. I think a lot of young people really enjoy that.
Yes, they do. They're weird. Okay, they're young. No, skateboard, definitely not my idea of fun.
Well, and then this place, Muizenberg, is where my Africa project is based. It's near Cape Town, right by the sea, and this water slide is very, very popular. So you climb up the ladders and you get up to the top, and there's water running down it all the time, and you whoosh down, going from your bends there are side to side and mostly down, but I think just behind the tower there's a little bit where you actually do go up, rather like on a roller coaster. And that's another very exciting thing for, well, children and adults too. But down in the right-hand side there, we come to something a little bit grim, actually. That's about warfare and firing a cannonball. And as you see in that picture, the soldiers in that cannonball are firing it over the top of the water to land in the city on the far side, quite a long way away, where it will, they hope, do some damage. And throughout, for hundreds and hundreds of years, well, not just in Europe, but across the world, people built forts or fortifications with high walls, and quite often on the top of a hill, often with a moat or water around them to keep the enemy out. So if the enemy was approaching and was going to attack, everybody would get into the city and behind the fort and behind the walls, and keep safe there, and probably fire arrows or even cannonballs out through the slits inside onto the enemy outside. So there's Warwick Castle.
What does this have to do with maths, Toni? This is very interesting. What does it have to do with maths?
Well, of course, it's all, again, what angle do you fire your gun or your cannon in order to hit the enemy? Again, there's maths behind it, isn't there?
Oh, and how fast how much force there is behind it. So how fast it's.
Yes,
the size of the cannonball, the weight of the cannonball, the shape of the cannonball.
You don't want it to land too short before your side of the wall, and you don't want it to go zooming over the top and out the other side. So it has to be carefully calculated. And I put that picture in again, and you can imagine there's some water there between the attackers and where the people they are attacking in the city or town behind the walls, and they want to get it up and over the walls and land in the middle there over the water. So there we are. So we've shown you a few examples now of different sorts of uses for the idea of a parabola and what's it doing. Now, what about the maths? Caroline asked a few minutes ago, what about the maths? Well, we have what we call equations in maths, and we have an equation which it defines the parabola, and it's what we call a quadratic equation. That simply means that it's got powers of x, x squared x, and just a constant number. So it's the path will be of the form y equals some constant times x squared plus another constant times x plus a constant, ax squared plus bx plus c. Or you might actually, instead of x, you might have decide that the best thing to do is to use the variable t for time. And then your position would, y, which is the height, would be given by at squared plus bt plus c, where a, b, and c are constants and t is time.
So there's nothing special about the x or the t. We just use t because it's a short letter to use for time. So we could use w if we wanted, or
yes, I mean
it's for eggs. If it was eggs we were talking about, we could use e.
Yes, I mean we tend to use a variable that to somehow makes you think of what the subject matter is, what you're applying this bit of maths to. And in this case, we're talking about the path of the ball through the air from t equals 0 when it gets either hit or kicked or projected from the gun or whatever it is, and as time in seconds maybe. According to how long it's been up there, its position will be given by that equation, and the equation I've described will of course be different according to those coefficients a, b, and c.
Okay, so the y and the t are variable, the y and the x are variable. They can change. So if y is one thing, x can be another thing, or the other way around, and the t, and whereas a, b, and c, they're constant. Those numbers, once within that formula, they don't change.
Yes, and y, we usually use the letter y for how high up whatever object we're describing is. Y is the height, and there you have the equation.
So the y is the vertical line, and the x is the horizontal line in your graph.
Now, after the break, we're going to do some mathematical gymnastics.
Excuse me, we.
Well, I hope Caroline is going to do these gymnastics, and what she's going to do is to use her arms to show us some graphs after the break.
See you after the break. Right, I'm ready, Toni. I've got my scene set here.
Well, we're going to talk about the slides first, Caroline, and then you're going to do it. So you're not going to do it yet, okay?
I have to move it around anyway, so we're good.
Oh, you're ready, right? So what we'll do is we'll talk about these slides, and then Caroline will lead you, and we hope you'll be able to stand up, get into a space, and follow what Caroline is doing. Now, it's a really good activity for children. I mean, it gives them a chance to get rid of some of that fidgetiness that children have. They don't really, it's not easy for them to sit still for a long time. And they're learning something while they're doing this activity. The idea is you need some space for this. And so you could take, if you're a teacher, you could take your class outside, and that it would be good. You don't need to write anything down. This is all done by copying the leader, the teacher, or teacher can ask somebody else to lead, and making the graphs with your arms. So at the front, the leader has his or her back to the class so that everybody is doing exactly what the leader is doing there. Everybody's looking in the same direction, including the leader. And the leader calls out the equations in turn, and everyone uses their arms to make the graph for that equation. Now, what I've written down here on this slide is some equations of straight lines. So we've got y equals x and y equals 2x. And Caroline shortly is going to show you the difference between those. And then y equals 2x plus 3, and where you stand on tiptoe, because now it's the same as y equals 2x, but it's raised up 3 units. That's what the plus 3 does. And then for the 2x minus 2, you bend down. So you can see those little pin people on the right. One of them is standing up on tiptoe and the other one is bending down. But in both cases, their arms are in the, looking the same angle. Although they're facing us actually, because if they were doing 2x and they were facing the other way, their arms would be tipped the other way. So I think those people are actually facing us. And then you've got minus 2x minus 2, and that's Caroline will show us later. The next one is a bit different because there's no y in it. It's just x equals 2. So that line, x is always 2. It never changes. So whatever y is, x will still be 2. So it seems as if that must be a line that goes vertically straight up and down through x equals 2 on the y-axis, and doesn't y for every value of y x equals 2. And then x plus y equals 3, that again is in a different, looks different from the others. So x plus y equals 3. So Caroline, give me 2 numbers that add up to 3.
2 and 1.
Okay, so x could be 2 and y could be 1, or the other way around. One of them might be a half, and the other one could be 2.5. They don't have to be whole numbers.
Yeah.
So we're not just thinking about whole numbers here. We're thinking about all the numbers possible. Well, of course, our arms aren't that long, but we're thinking about a whole lot of numbers. So let's move on. And these pictures are rather different. So now what Caroline is going to do is to stand with her feet together, because what we thought was it was actually better to have your feet together and your body being up and down, being the y-axis, and your neck being where the origin is, and so across the tops of your shoulders being, when you stand just ordinary, not on tiptoes, not bending down, that be the x-axis. That's probably the easiest thing for the children to model. Now this is a graph that a lot of people don't know about. So these 2 bars, these vertical bars, and not brackets, they're just vertical bars, they mean the modulus. So as you see, the first picture, the woman there is got both arms raised and they are straight. Now, what she is showing you is with one arm, she's showing you y equals x. That's clear because the y equals x has to be halfway between the x-axis and the y-axis. But the modulus means you have the positive value. So modulus of 7 is 7, and modulus of minus 7 is also 7. And that's why she's got both of her arms up, because the modulus of a number is the positive, the equivalent positive number for that number. So it's always, modulus is always positive. And so if the modulus is always positive, for the lady on the right, the lady in the middle, minus modulus of x is always negative. What's standing there between those two vertical lines is always positive, so minus it will always be negative. And then the one on the right, oh my goodness, it's the same as the one on the left. Modulus of x is the same as modulus of minus x. Why? Well, because it doesn't matter what number x is. It could be positive or negative. This modulus always makes modulus, the answer, the value, positive. So she is raising her arms because all the values are positive. So we've done straight lines there, including the modulus being straight lines. And then before I stop sharing and let Caroline show you some of these graphs, we're going to show you these, and then Caroline will start showing you some more. Now here, these arms are not straight. She's got her arms curved. And y equals x squared. Oh, this is a parabola. In fact, they're all parabolas. So you see the same parabolic curve, but the simplest of parabolas because it's just y equals x squared. Y equals 2x squared. So what's the difference there? She's got her arms up a bit higher, so it's a steeper graph. So if we take the straight lines y equals x and y equals 2x, y equals 2x is steeper. And here it's the same with the parabola. It goes up more quickly. It's a sort of steeper curve. And y equals a half x squared, on the other hand, if you compare the graph on the extreme right with the one on the left, she's lowered her arms and made the parabola shallower and wider. So that's y equals a half x squared. So what do you think, Caroline? Are you ready to go?
Yeah.
Okay, so I'm going to stop sharing. Okay. Now, Caroline is going to turn round in a minute because she's going to be leading us. And if you want to join her, you just do what she's doing, right? So Caroline, show us the positive direction of the x-axis. That's the positive direction, and it's marked on that black screen with a horizontal line. And what's the negative direction, Caroline? Okay, so that is, as you would see on a graph drawn on graph paper. If you were looking at it on a piece of paper, those would be the positive direction of x and the negative direction of x. Now, Caroline, unlike the lady on my slide, she's going to stand with her feet together. It might be a little bit more difficult to balance a bit, but she's very supple, and you're going to manage beautifully, aren't you, Caroline? So her body is straight up and vertical, and that is the direction of the y-axis. So her head, that is pointing upwards. and above the 0, and that's the positive direction, and the negative direction is downwards. Okay. Now the origin, we call it the origin, is the point 0, 0, and that's somewhere when Caroline stands there, just about where your throat is, isn't it, Caroline, more or less? Yes, sort of, yes. And then, Caroline, put your arms out. You'll see Caroline's arms are going to be along the x-axis. But when she goes down, the x-axis won't move. Caroline's arms are not the x-axis. The x-axis is what you see on the black screen. And Caroline's arms will go, oh, she's going down now. Now she's actually showing us y changing. So go down again, Caroline. And that horizontal line now is about y equals -3. Now she goes down a bit more, y equals -4. She's trying to hold her arms straight out, showing us the lines y equals constant. How about before the break showing us a line x equals constant? What about x equals 2? You've got a point 2, 2, 1 there. Right. You need to get from the way I see it, Caroline, your arm needs to go back and up a bit, back towards your ear and up a bit. That's better. Now her two arms are now going straight up and straight down, and she's moved a bit to the right, and x equals 2 everywhere on that line. If stand back, Caroline, and show everybody on the board the point 2, 1, right? So Caroline was standing in front of that point and showing us the line x equals 2. Brilliant. Caroline, it's time for our last break. So afterwards, you can do the other.
Okay, yes. See you after the break for some more maths aerobics.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us, yeah, 24 hours, and let the happiness come to you on Relax Radio. Tune in to Relax Radio. Relax Radio.
I've got
Brilliant.
Tony, in case I need to go any higher.
What?
I brought my ladder in case I need to go to
So do you want to get in position now, leader, and show everybody? Are you all ready? Are some of you going to do this with Caroline? Caroline, what about y equals x? Yes, brilliant. Now that line should be 45 degrees, and it's pretty good. What about y equals 2x, Caroline? That's steeper, okay? What about y equals a half x? And now y equals 2x again. Now do y equals 2x plus 3, Caroline. On your tippy toes.
Well, considering that is 1, I have to be here. So
Yes. Right, y equals 2x plus 3, more or less. Okay, Caroline, what about y equals 2x minus 2? So she's going down. Well done, lovely. Okay, what about minus 2x, Caroline?
Forgotten. My brain's not telling me that one.
Oh, you tip it the other way. Top left to bottom right. Yes.
Minus 2x or minus...
Well, I said minus 2x.
Y equals minus 2x. Got you. Minus 2x. Okay. Got
That's it. Fantastic. And what about y equals minus 2x minus 2? She's going down. I think she's doing the splits now. Fantastic. Okay. Very, very good. Now then, we're now going to do those funny modulus V's. Okay. So first one is y equals mod x. Remember, it's always positive. That's it. It's right. It goes in the first, well, in the positive quadrant, it's going up towards plus infinity, and in the other quadrant, it's also going up. Okay. So that's mod x. What about minus mod x, Caroline? There you go. So that's always negative. And Caroline, what about the modulus of minus x? Okay, that's positive again. Okay, so you can imagine yourself there as the leader with your class and them all following on and doing these graphs. Another way you can after you've done this a few times and the class are quite used to it, you can do the graphs and get them to call out the equation. So that will give them a chance to think more and tell you what you're actually doing.
And all we've got here is a sheet with some tape stuck to it.
You don't even need that, though. You can just imagine it.
Okay.
We thought it would be probably quite good for this demonstration, but you don't absolutely need the sheet. You can imagine it. Now, Caroline, I think we should have another break before the end, don't you? Or not?
Right. Time for a break. I don't know. I thought we'd had 3 breaks.
Oh, well, we don't need another one then. Sorry about that. The next one is, okay, Caroline, get ready for this. This is y equals x squared. It's a parabola again. It's a curve. There you go. Nice rounded curve. And what about 2x squared? Oh, okay, that's a steeper, still a curve, but steeper. And y equals a half x squared. And that's still a curve, but much shallower now and wider. Great. Now that was to the power 2 x squared. What about x cubed? Y equals x cubed. So if x is negative, then this is like minus 2. It's going to be minus 2 cubed would be minus 8. So Caroline's showing you it's going, her right arm is showing you a curve that's going upwards, and her left arm is showing you a curve that's going down. So in that quarter or quadrant, the terms are negative. So that is x cubed. Now, Caroline, what about minus x cubed? Yes, you've got to make a curve with your right arm as well. Yes, well done. Minus x cubed. Beautiful. And the last one is x squared plus y squared equals 4. And this is a circle, and Caroline, you've got to duck down a bit so the center is at the origin. Okay, now try and make your arms into a circle. They're a bit angled at the elbows. Okay, she's making a circle now. That's x squared plus y squared equals 4. So that is our graph workout, or yes, your exercises with graphs. And Caroline is giving you a bow. Well done, Caroline. So I think that's a lot of fun for children. We were talking about sketching graphs earlier, weren't we, Caroline? And
yes.
It's important for children to know the shapes and properties of the graphs, and to be able to sketch them without plotting points. They see something like y equals x cubed, and they should immediately know what shape it takes. They shouldn't be thinking, no, I've got to plot points, where does it go? And this sort of exercise helps them to become familiar with the shapes and what it means when you change the coefficients, the numbers. And
it could be a little bit like the times tables. There are things that you can work it out, you can plot it if you know it, and that's something that this has been really helpful to me, because I had forgotten, and I never really knew the graph shapes, but know them like the times tables. But this has actually been lots of fun, and it was like a hole in my knowledge, which I'm really pleased to have a way of filling, and that would apply to many primary teachers, to be able to fill. I mean, I know a lot of these curves are relevant to secondary, to 11 plus children, but it's a good thing for grown-ups to know, especially for the teachers.
Well, the thing about it is that when you plot the points, you're only plotting some of the points on the graph to give you a reminder of what the graph ought to look like. You certainly don't join with the curves, you don't join them with the points you plot with straight lines. So that would be a bad mistake. As far as the straight lines are concerned, how many points do you need to draw a straight line?
Oh, that's easy. Do you want me to?
Two.
Yeah,
just two. Yeah. And so if you've got an equation, you
have to know that it's a straight line. So
yeah.
In order to be able to join those two dots, you can't just say there's 2 points on a graph, let's join them with a straight line. It depends on the shape of the graph.
Oh, of course, yes. But if it's, yes, so that the first thing is to understand. I mean, maths and science use graphs a lot. And you need to be able to use the maths that you learn in school, you need to know and have a good feeling and understanding of graphs and the equations of the graphs. It's related to functions, which is all about how the x value changes and what happens to the curve, the points, as the variable changes. Now, if it's linear, if the highest power of your x is just to the power 1, then it will be a straight line, and you need to know that. Okay. Now, we were talking a lot earlier on about curves of balls in the air, and of not just balls, but the arrow if you were doing archery, or even the human body if you were jumping, either a high jump or a pole jump over something, or horse jumping again. All of these, the path in the air is a curve, which we were saying is a parabola, and that is of the form something times x squared.
So, Toni, something that while I was doing a little bit of research about roller coasters, I spoke to someone from the Ferrari world in Abu Dhabi, and he said that the only thing he could think of that was parabolic was the lamps that light, the actual lighting with parabolic lamps. And then I'm like, okay, so how do we connect with that? Well, we're only talking about the X and Y axis here. So we would be looking at a cross-section of a parabolic lamp here. We're only staying in 2 dimensions. And when you mentioned the 2 dimensions of the path of the ball, that would be like not including any influence from wind or anything like that.
Yes, it's traveling in a plane.
It's assuming 2 dimensions. So that was
that's true.
You can have parabolas that are 3-dimensional parabolas, 3 parabolic shapes, like a telescope.
A paraboloid, it's called, Caroline.
Thank you very much. I didn't know that. Paraboloid.
If you have a parabola and you rotate it round, you get a paraboloid. And the brilliant thing why they're used for lamps is that there's something in the middle of that paraboloid shape, which is called a focus. It's a particular point, one point. And if you put the light there, then the light is reflected off the paraboloid shape, and it comes out in parallel lines. So that's another property, a brilliant property of the parabola, that it has a focus.
And in 2 dimensions, the same would apply. That if you took a point, that point in 2 dimensions, and took it out to the parabola, and drew the lines, they'd come out in.
Yes. So what you get when you get a reflection is what they call the angle at which you hit the surface, and you come off the surface at the same angle on the other side. And when you do that, the parabolic surface, or even just an edge, reflects the light in a horizontal line, parallel to the axis. Actually.
And the people that play pool know that.
Yes.
In principle, where you play pool, you hit it at a direction so that it comes out at the same angle, but in another direction.
Oh yeah, that's the angle of incidence and the angle of reflection. Yeah.
Right. And so it's the same principle but I just thought that was lovely that we're talking about 2D, but of course it works in 3D. We are specifically talking about a slice of a paraboloid.
Yes. And then we went on to do x cubed, but we didn't do x to the 4th, but Caroline could have done x to the 4th.
X to the 4th. Let me remember what x to the 4th is. Oh dear. Wait a minute. X to the 4th. X to the 4th. X to the 4th. X to the 4th. Wait. That's x squared. No, it's gone. What's x to the 4th?
It's steeper than x squared.
What's the difference between x to the 4th and 2x
steeper?
Squared?
Yeah.
Even steeper.
No, it was all right the first time. It was just steeper than x squared. Yeah.
Right.
But it's you see, if you've got the 4th power, Caroline, it's always positive.
Exactly. That's why my arms both went up. Did you notice?
I did. You knew what you were doing. Yes. And if you've got an odd power, then one arm goes up and the other arm goes down.
And you get to.
Yeah. And if your children have done this, they will know these shapes. They just need, practice a bit. It's a lot of fun. It gets rid of those fidgets. It gives them a little bit of exercise. You only need to do it for 5 minutes and then back in their seats and back to concentrating. And if you've got enough space in the classroom.
And it helps them remember them. It's like, whoa, where's the downside?
I think our time is up, Caroline.
I think it is. I think you're right. Well, we've got like a few seconds. So thank you very much, everybody. We'll be back next week, 5 o'clock London time, with Toni and Caroline, with some other, think of any more crazy antics we can do with mathematics.
Yes, we'll try and do something practical again.
See you next week. Thank you.